Thank you, Dr. Sushmita and Dr. Mahesh and everyone here. Good afternoon to everyone. And I would like to share my screen. Is my screen visible?
Yes, ma'am.
Okay. So I go to the slideshow mode. So today, this topic is going to be on solar flare and its analysis using sunpy. And we will begin just with our solar system, which is gravitationally bound system of sun, and it has planets and asteroids and indirectly moons also. It is one of the many million solar systems in the entire Milky Way galaxy. And we all know that it has been 4.5 billion years approximation. Then when a cloud of interstellar gas and dust collapsed, resulting into solar nebula, and it is located in the Milky Way Orion Spur cluster. When we are talking about sun, then we are talking about its perspective to the current scenario. Many civilizations have called it by different names, including Egyptians as Ra, Greeks as Helios, and Persian as Mithras, and our Indian name that is Aditya or Ravi or Surya. And when we are talking about Aditya, the Aditya mission is something which will provide excellent opportunity for those who are working in this field to have enough data. And I think it is going we are going to get huge amount of data from the Aditya mission that will provide ample opportunity for looking at and analyzing at the data. In this case, when we are talking about the sun and we are talking about the solar flares, all the radiation, visible radiation, comes from the photosphere. And above the photosphere, the layers of the atmosphere of the sun has two distinct layers, that is the chromosphere and corona. And aim to understand and characteristic features of these layers would mean that we understand the interaction of the sun's magnetic field with highly mobile charged particles in it, which gives rise to a variety of observable events, and these events are collectively known as solar activity. And in this case, the theoretical analysis of interaction of magnetic field with the conducting matter in motion is known as magnetohydrodynamics, and it provides basis to understand the solar activity and the related features of the sun. And when we are talking about heliosysmology, which also provides valuable information about the sun's internal structure. So when we are talking about the sun as a dynamic sun, because it keeps on changing all the time, we have got terminologies when we are talking about emissions from the sun, and those are some of those illustratives are solar flares, coronal mass injections, prominences, and filaments. So when we are talking about, we are not going to talk about all of these, but we will be talking about solar flares. And in that, the topic will revolve around what solar flares are, what are their types, their causes, mechanisms of their occurrences, and their consequences on the planet Earth and on us, and the observations. What are the missions or observatories which are doing these observations on solar flares, and a computational analysis using sunpy, which is also one of the versatile application of analyzing solar flares. So in this regard, solar flares are the abrupt and localized emission of electromagnetic radiation in the sun's atmosphere. Where are these originating from? So we will, Professor Rajmal Jain, we had a lecture by him, and I think everyone knows about the many activities which are occurring on the sun. So when we are talking about their origin, the active regions play a very important role in that. And in active regions, when we are saying there are identification of the active regions, their naming is done by NOAA, and then their progression is also seen over the period of time. Many a times these are accompanied by CMEs. It is not always that a CME will be accompanied by a solar flare, but that also happens many a times. And in that, solar particle events and solar phenomenon take a important different direction as compared to the ones which are only with the solar flares. So we will also try to see that what is the impact of the solar cycle on the solar flares. Is it the frequency proportional to the solar maxima and minima? Because in this particular case, the solar cycle also plays a very important role on their occurrence. In this regard, when we are talking about the solar flares, how do these occur? So these are attributed to the reconnection of the huge magnetic field in and around the sun. And indeed, these are associated with the active region, often seen as sunspots, where magnetic fields are strong and a change in the accumulated magnetic energy in the sun's atmosphere is the one which causes acceleration of charged particles in the plasma, and that causes emission of EM radiation across the electromagnetic spectrum. So when we are doing classification of solar flares, in that case, these are classified according to their peak brightness in the X-ray wavelength. When we are talking about according to they have got different classifications, and one classification goes according to the GOES observatory. In that, it is like a Richter scale in that the B ones are at the bottom, and 10 times B will be equivalent to a C type of a flare, and 10 times C will be a M type of a flare, and 10 times M would be a X type of a flare, and these are on the logarithmic scale. So it means that when I'm going to have a flare which is M10, that will be approximately equal to X1. So my question would be to everyone would be, if there is a tenfold increase from one class to another as we are moving from B to X, say type of flares, how much is a X class flare in strength as compared to a B class flare? So I would request everyone to write the answer in the chat so that we can we can proceed further from there. So we are getting an answer of 1000 times. But try to see that in case we are talking about x1, x1 is the starting point of x. It can end at x10. So x10 would mean that from b1 to x1, they will be even more than 1000 times. Because of that, x can vary from x1 to x10. So in this case, why there is the two major important classes are M and X types, which can cause short radio blackouts at the poles and minor radiation storms, which can risk the astronauts also. The intensity can vary from extreme ultraviolet to X-ray radiation for these flares, and sensors get saturated beyond a certain limit. And these measurements are not quite straightforward. In 2003, a powerful flare occurred, which was estimated at X45, that means X4.5, and the cutout value was X17. The transmission issues and global blackouts may happen at that particular values of the values of these flares. So when we talk about the GOES class, GOES class, in that case, these are depending upon the intensity profile, that is watt per meter square. A class flare would be less than 10 to the power minus 7 watt per meter square. A B class is classified if its value is in between minus 10 to the power minus 6 to 10 to the power minus 7. C class would mean in between 10 to the power minus 5 to 10 to the power minus 6. And if it is in between 10 to the power minus 4 to 10 to the power minus 5, then it is called a M class of flare. And if it is if it is going to be after 10 to the power minus 4, then it comes to the X type of flare. So one can see in this diagram that these are labeled as, depending upon on the x-axis, on the y-axis, we have got the watt per meter square, and here on the x-axis we have got the time, that is the universal time. According to the intensity, the labeling of these flares is done, and the X1 is definitely showing a much more intensity as compared to the flares, which are going to be M1, M2, and C9, C3, and C2. And this, please note that this is a logarithmic scale. So in this particular case, we have the classification of the solar flares, which are occurring and which are observed on day-to-day basis. When we talk about these in terms of energy, then one unit is also used. A normal flare will release approximately 10 to the power minus 30 erg of energy, which is also in terms of joules can be calculated. And this is the kind of energy which is equivalent to 1 million volcanic eruptions or 1 billion hydrogen bombs. So in that particular case, that is why monitoring these is also going to be a very important thing, and the space weather predictions are done based on the intensity of these flares, which are measured by different devices. So when we talk about the classification of solar flares, it would mean that these are identified. There is an increase or the rise time, which may last for minutes, a temperature in the range of tens of millions of degree Kelvin. There can be a series of intense radiation of EM spectrum and ejection of high energy electrons and protons in the interplanetary space. When we are talking about the missions, international missions, which are there to measure the solar flares, there is one mission that was in the year 1991 to 2001 to just mention, that was called Yoko mission, which means sunshine in Japanese, and it targeted at high energy solar physics. It included on board hard X-ray telescope, that is HXT, a soft X-ray telescope, that is SXT, Bragg crystal spectrometer BCS, and wide band spectrometer WBS. And in this particular record, this is the website which can be accessed for seeing that what kind of data is available on that. And I would like to show a movie which would say, which can show that how does there is a changeover when there is a sun minimum and sun maximum. What happens to the corona at that particular point of time, and what happens to the sun, because the sun is at a very less active state when it is minima, and the number of solar say sunspots are also very less. But when it is in the maxima, one can see an enhanced activity, and that is something which also, that is the time when there are more intense solar flare which occurs. And this session in the month of May, we were approaching the sun maxima, a maximum activity, and they were up. It was like a rapid fire of these particular solar flares in that range in of the higher intensity, and that is what is observed when these kind of things happen. So I just run this movie for 2 minutes, for a few seconds. Is the screen visible and the audio also visible?
Yes, audio is visible.
Okay. So one can see here a solar minimum between the activity cycle 22 and 23. It
Uh,
was taken at soft X-ray wavelengths in May 1996. The X-ray corona is quite thin as compared to the periods of high activity, and it is a good time to see the tiny X-ray bright points whose frequency is fairly independent of the sunspot number. So the thin A thin layer of corona is visible in this particular case as compared to the one which is of the higher activity. So in the solar, I can go to the next slide in which the solar maxima is there, and one can see how the sun activity gets activated to a higher extent during this time. So one can always note that. And the dynamic sun can be seen with more vigorous activity as well as a very thick corona which is surrounding the whole sun. Is it visible to everyone?
Yes, ma'am.
Thank you. So moving further on, when we are observing sun, why do we need different wavelengths for observing sun? In the case of sun, the temperature plays a very important role. So yellow light from sun surface is reflective of temperature, which is approximately 5700 degrees Celsius in that vicinity. Extreme UV is by atoms at a very, very high temperature, which can be seen in a wavelength of 9.5 nanometer, which is 95 angstrom. Movement to know about how heat and particles move through the sun's atmosphere. Extreme UV is a good wavelength for studying flares at high temperatures. And all these information can be seen at NASA website, which is showing that why there is a need to observe sun in different wavelengths. In this regard, it is also important to see why this is not going further. Yes, just a moment. And so there is a mission by which is called SDO, in which 4500 degree, the 4500 is the sun's is used for sun surface or photosphere. 1700 is used for surface and chromosphere where T starts rising. And 1600 is used for upper photosphere, which is also called a transition region, which is in between chromosphere and corona. And in this particular region, the temperature rises very, very rapidly. 304 is used. This is the light from chromosphere and the transition region. And 171 is corona. When quiet, it shows huge magnetic arcs known as coronal loops. 193 is used for slightly hotter regions of the corona and much hotter regions of the solar flare. 211 is the wavelength which shows hotter, magnetically active regions of the sun's corona. And 335 is the wavelength also shows hotter, magnetically active regions in the corona. And 94 is highlights regions of the corona during a solar flare. And 131, the hottest material in a flare. So depending upon the requirement of looking at different temperatures or different magnetic domains within the different parts of the sun, different wavelengths are used. SU is a solar dynamic observatory, which is also observed a mid-level level of flare on, say, November 13, 2012. This photograph shows that. So it also shows that how much intense for disturbing the atmosphere in the layer of GPD and communication it causes, and this disturbs the radio signals far as long as duration of a particular amount, and M6 is the minimal which can affect the space weather radio communication. Radio blackout occurs according to the National Oceanic and Atmospheric Association, that is called NOAA. That rates the weather scales from R1 to R5, and if the flare is of the level M6, that would mean that there is a signal warning of R2, which means moderate. And if it varies from R1 to R5, depending upon the nature of the flare. T01 also, which shows the light from the region of the sun's atmosphere where flares originate. And in this manner, there are different things which can be observed. So one can see in the different wavelengths of these three figures, there is a prediction, there is a depiction of a flare which is originating, and that in this particular case is a mid-level flare of the say order of M6. So how these impact us is because these are absorbed by the upper atmosphere, especially the ionosphere, and cause interference with the short radio wave communication. The intensity can vary from extreme ultraviolet and X-ray radiation from the solar flares. That is why these monitoring of these flares is very important, and not only from just protecting us from these and for the precautions, taking precautions in case the pre-warnings can be done, but also to understand the mechanism in order to understand how these are getting originated and what kind of information regarding the other parts of the sun can be made out of it from where it is originating. So familiarization with sunpy would mean is the second part of the talk, which says that this is how we can analyze these kind of flares and how other kind of data can also be done using that. So why we are talking about sunpy here? Because we all know about now Python libraries, which are there for many other applications. Like we know about SciPy, we know about Matplotlib for plotting, and other AstroPy was also introduced. Same way, SunPy is also something which is an open source Python library used for solar physics, which is free also, and it was established in 2011. Now it has matured to 14 more years. It consists of a large community of researchers, developers, and enthusiasts, and it is designed for both beginners and advanced researchers in the solar science. So when we are talking about SunPy, why do we use it? It facilitates acquisition, analysis, and visualization of solar data, access to a wide range of solar data sets, and it supports reproducible research and collaboration. And challenges in the solar data analysis are huge. Why huge? Because there is a large volume of heterogeneous data which is being generated, and it needs tools to process and visualize complex data sets. And the three challenges of the big data are the three V's, in which volume, large amount of data, is something which is of consideration. Velocity, and that is for the real time data analysis. And variety, because there can be many data sources which are there and one has to access data from all of them. And that is why these three V's are of great importance when we are talking about big data. In this case, familiarization of SunPy would mean that we also know about supported solar observatories and data sources. One such observatory is GOES. GOES is Geostationary Operational Environmental Satellite, in which solar X-ray and extreme UV data is of importance, and event list for the solar flares. SDO is Solar Dynamic Observatory, which has high resolution solar imaginary and time series data. SOHO is Solar and Heliospheric Observatory. Observation of the sun's corona and heliosphere is done under that. And RESI is the Reuben-Ramati High Energy Solar Spectroscopy Imager. High energy solar flare observations are done in that. And other data sources could be solar orbiter, Hinode, and ground-based observatories. So when we are talking about SunPy, it is also important to understand the data types. Data types could be image data. Image data can be high resolution solar images and multi-wavelength observations. We just saw that why multi-wavelength observations are important when we are talking about the analysis of the sun's data. And the time series data would mean that the solar irradiance and the flux measurements and temporal evolution of solar events. They can be spatial evolution can also be there, as well as the temporal evolution of solar events. In event list, there can be solar flare occurrences, coronal mass ejections, to name a few, but there are many more beyond that also. And derived data product would means that brightness maps, peak detection results, etc. And all for all this, the data is collected in a manner that the pre and the post data is also analyzed in order to see the impact of a particular occurrence or a particular event which is occurring on the sun. So in this regard, the key features of the sunpy are data query and download. And so we can access data sets from multiple solar observatories and seamless integration with a virtual observatory. And the virtual observatory in this case is called VSO. Data analysis would mean map projections, coordinate transformations, and overlays. Overlays of different multiple wavelengths or multiple data from different instruments can be overlaid in that respect. And time series processing and peak finding. Whensoever I just explained that when we are talking about the solar flare, it may last for few minutes to some few say fraction of minutes to few minutes. In that case, there may be a rise time, there may be a peak time, there may be a fall time. So all these information is sorted with the help of peak finding and peak maxima, or otherwise the peak duration of a particular event. And visualization would mean that the plotting of the solar images, time series, and the annotated maps. In this particular case, community and extensibility also plays a very important role, because the user contribution, it is an open project, and the user contributions are always updated with the passage of time, and modular design for integrating with other tools. So all this, because in the recent, there are efforts to say utilize few of the astropy functions with that of the sunpy, and those things are going ongoing, and which are enhancing or increasing the versatility on and the applicability of a particular application. So in this regard, example use cases for what purposes sunpy can be utilized. So these are just illustrative examples in that studying the solar flares. As I explained that GOES observatory data can be analyzed for GOES flare events and visualization of the temporal trends. Solar imaging analysis. Suppose we want to know in a particular solar activity which one is the brightest area of that particular on the solar disk, and that can be done by identifying the brightest pixels on that particular image. So identification of the bright regions in the solar images and studying of the spatial feature of the solar activities. In this regard, the time series analysis would enable detecting of the peaks in the solar flux data and correlate time series with other observations. So here, the sunpy package has got different modules, and those modules can be called in for different applications. So those are sunpy.coordinates, sunpy.data. For image processing, it is sunpy.image. For utilities, it is sunpy.util, and sunpy.time is also there. Map, sunpy.map is another one. Sunpy.physics is another one, and sunpy.visualization, sunpy.net is used for remote data, and sunpy.time series. These are just few which are available for usage in the sunpy, which can be utilized, and we will see an example of that in the forthcoming few minutes. So we will be getting familiarized with sunpy with first case study, which is querying the GOES event list, and the learning objective would be to run a query and explore a solar flare event using the GOES database. And the key steps are going to be, first step would be to import required sunpy modules. Second step would be to specify query parameters. Query parameters are going to be the time range, event type, etc. Event type would mean that flare is one event type. CE is another event type in which the coronal mass ejections is happening. Same way, time range. Suppose I want to find the time of the occurrence of a event that is a flare that occurred between yesterday and today. So how would this is the way I will specify the query parameters. Execution of the query is done using FIDO, and analysis and visualization of data, event data, is the next part of it. So please get ready, all of you. Open your collabs and follow the instructions which I am going to give in the next few minutes. So I will request everyone to those who can open their collabs can start working along with me. Do we have someone few who can run alongside that? Please write yes, yes, okay, good, very nice. Is it clear up till now? Okay, thank you. Okay, so I'm getting back to my slideshow. So first thing is that we will be installing the required say libraries or the relevant libraries and the dependencies in the Google Colab. So here this exclamation mark is used in which when you are running it locally, actually then it can run on the terminal. So exclamation mark pip install sunpy. Again, exclamation mark pip install zeep and exclamation mark pip install drms. So please write these three in the Google Colab. Those who are not able to run it now, they can always note down the instructions and then they can run later. And if they face any problem, they can get back to me and I will be happy to help them. So here, after, do we have a few who have already run this? Yes, somebody has raised hand. Next step would be, after you have done that, next step would be, here we will be using FIDO. We will be importing FIDO. So FIDO is a unified data search and retrieval tool. It provides a simultaneous access to a variety of online data sources. So it's like a search tool, data search tool, which is a unified tool as well as a retrieval tool, and it can simultaneously, so many data can be accessed at the same time. So from sunpy.net, import f capital F IDO. And second line would be from sunpy.net, import ATTRS as A. So A is a brief, say, symbol in order to import all the attributes of this particular requirement. So A is for the brevity. We can write A dot time, A dot things like that. So do we have anything who has, everyone has done? Done. Okay, fine. There is a question by, there is a comment by Akash Divedi. Can we get data on different magnetic fields due to the dynamics of charges in plasma or surface of the sun, or amount of radioactive in particular region? We can do the magnetic mapping of the sun these days, and that is possible. And that analysis tells us that how does the magnetic field vary before or after the flare. So that can be done. So that is done by in a particular wavelength, and there is a particular software which analyzes that kind of a data. I hope I have answered your query. Has everyone done up till this point? From sunpy.net imports ATTRS as a A. and all the installation of the relevant libraries followed by importing of the FIDO. Yes, you have to make a new collab live file of your own. Yes, Malvika, I will explain again. I have explained that which files to which libraries to import or install and which one to import. So there are three which I have written in the top, and I have written that import FIDO, and FIDO is a unified data search and retrieval tool, and it which can provide a simultaneous access to a variety of online data sources. Okay, so this after doing this, I go to the next slide. In that, what we are doing, we are we want to know in a particular time domain or in a particular time how many flares occurred which were of intensity greater than M1.0. So we will write event type to be FL. FL is for the flares. T start. T start is in the format of year, month, and date within the these quotation marks. So it is 2024 07 28 and T end. This tells us the end date up till which we want to search for a particular event type, which is a flare. And result is going to be fido.search a.time. TCT is in caps, and then in the bracket T start and T end. It has another attribute which is a dot heck event type and in bracket event type. Event type would mean that search of flares which are greater than M1.0. And in this case, a.heck.fl dot goes CLS is greater than M1.0 and a heck.obs.observatory is equal to goes. So please understand this very well that what we are doing. We are trying to find out an event type which is a flare which is greater than M1.0. One may ask why we are only asking for the flares greater than M1.0. I just explained that if there is going to be a moderate, say, warning, which is of the level of R2, when there can be some disturbance in there can be some blackout, or there may be some, say, phenomenon which is occurring because of this flare, that minimum range is in the range of say M5 to M6. So all the flares greater than M1.0 would mean that we are detecting flares which are more than 1.0 going up to M1 9.9, then all X flares also. And these are the ones which we would always want to know that if had occurred in any given amount of time. And especially, we would like to know that what kind of sun's, say, appearance in the form of solar maxima or solar minima is basically affecting origin of these kind of flares. So here we are interested in the T A dot time, where A dot time will have two parameters, T start and T end. So T start is our starting time, T end is the ending time. So I want to know about these flare within the time period on 27th of July 2024 to 29th of July 2024. So it starts at 12:00 time and until the next day. So it will give me only the flares which are occurring on 28th. That I will show with the data. And which observatory it is searching goes, where the recording for these flares is done. Is this point clear to everyone? I can check the chat for this if this is clear. Okay. Okay. So when you write heck results is equal to results heck. What is heck in this case? Heck is the heliophysics event knowledge base. So heck underscore results is equal to results, and in the square bracket you will write x heck within the double quotes, and then print results. So print results would mean that heck underscore results dot show. And what do we want? We want the event start time. When did a flare greater than M 1.0 occurred? Event peak time. When was the peak time of that event? Event end time. When did it ended? And FL goes class. What was the class of that particular flare according to the goes category that is there, followed by the NOAR underscore NOAA number. So that is the active region number which is released by NOAA, that is responsible for the occurrence of that particular event which we are talking about. So I will wait for you to write this code, every one of you to write this code, and then tell me that whether you are getting the similar result or not. I would wait for a few minutes. It is ATTRS. And those who are not able to get it, yeah, I can go back to the previous slide, not a worry. This one or the previous one. All of you can note down these. I could give the code in 1 minute. I can share this file, but I want you to write the code, come up with the difficulties you are facing while running it, what kind of syntax error you get it, and then overcome those errors and get the result. And don't worry, I will be happy to share all these slides, all these files. But if you try once on your own and overcome all your difficulties and all your errors, I think that will be more meaningful. That is what I feel. So I would request you to kindly run the code if you can right now in this limited time. Otherwise, you can always take it from me and you can run it. Not an issue. Don't worry in case you are not able to do it, but in case you are able to do it, I think that is wonderful. And this example I have taken from the sunpy library only, so you can always go and search more things also over there. So I acknowledge the sunpy library for this, and sunpy website, that is sunpy.org, and everyone can look all these as a sampler cases, tutorials given over there, and try to understand the code and run it for different other applications also. Is there anyone who is able to get this result? Oh, Himanshu, thank you. Yes, Rohan, it will be better, but I think the font size I have enlarged too much in this case so that one can see that very easily, and I am holding it for some time. I think it can be any way through which you can. So some of you are able to get it, that is wonderful. And those who are not able to get it, they can always check it and they can see where they are getting the error. I can show it again. Okay. So there is a recap now. Install the libraries of SunPy, Zeep, and DRMS. Then import from this sunpy.net, import Fido, and from sunpy.net, import ATT as A, followed by select the event which you want to search for. That is event underscore type. This is event underscore type is a dummy name. You can name it like anything, but in the bracket you have to write FL. That is the flare. And then you have to give T start and T end. And then in the result, it is fido.search, a.time, T start and T end are the parameters, a.heck.event type, and in the bracket, it should be the same thing which you have written here. Event type and this event type should match. And then a.heck.fl.goes, GOESCLS. These 5 letters are in caps, and then LS are in small caps, and greater than M in the within the quotes M 1.0. And then a.heck obs.observatory is equal to GOES. So we are taking data from the GOES observatory. Okay, accessing data from there, followed by printing of the result, and output should be event start time, event peak time, event end time, and the GOES class of the flare, followed by the active region number. So those who are getting it, it is fine. Otherwise, they can wait for this to be shared. Bhulesha Nivedita has got it. Himanshu has got it. Himanshu Sharma. Mani Kantan has got it. Nayan Patil has got it. I can make it a full screen, no worries. Is it okay now? Siddharth also has got it. Got it. Okay. So should I wait for some other time? And yes, Palak, your question is why we took M1, all these greater than M1? Because for space weather forecasting, the peaks greater than M1 are of more significant in terms of their impact on our interplanetary space, as well as on the planets, as well as on the communication system, on GPS. All these are of more significance than the B and C type of flares. The above have got the same result. That is good. Okay. So I think I can move forward so that we can do another case study also. And then you can go to the website and you can see many other examples, and that will give you a hands-on is, I feel, is more important here. And if you try something on your own, you will always, I think, remember it. So that way, with understandability that what each terminology or each part of the code is doing. Is that right? So moving further on, the second case study we can follow. Case study 2 is the finding the brightest pixel. So learning objective is going to be locating the brightest pixel in a solar image. So the task is going to be, key steps are going to be load solar image data using map. So in this case, we will be using MAP, map. Identify pixel with the maximum brightness. and plot results with overlays. So in this case, again, I will be using one sample image from the library of the sunpy itself, but you can always download more images in different wavelengths in order to see that how does the data vary from one case to another case. So in this case, import relevant libraries include sunpy.map in this case and a sample data image from AIA. So that is another thing which we are going to do. So here import matplotlib pyplot as PLT, import numpy as NP, and import astropy.units as U, and import sunpy.map, and from sunpy data sample import a image AIA 193 underscore image. So this is available in the library of the particular say it is already available there. One can utilize this for utilization. So from sunpy.data.simple import AIA underscore 193 underscore image. Is it done for some of you? Next part is going to be to convert the sample file to a sunpy map object. So in that case, we will be storing AIA is equal to sunpy.map dot. Please see the spelling here. Here it is in the lowercase map, and then dot map is in the first letter is in the uppercase. And what we are going to do that of the image which we had selected for finding the brightest say pixel. So that is AIA underscore 193 underscore image. So in this case, find the coordinate of the pixel with the maximum brightness is the task. So here, pixel underscore pos is equal to np dot arg where aia dot data is equal to aia dot data dot max star u dot pixel. So what this command is doing, this command will use the data stored as numpy array, and this has to be multiplied with the units of pixel because the next line uses u dot pixel for the further processing. So in this case, we have to find the coordinates of the pixel with the maximum brightness. And this command aia.data.max is actually searching the data with the maximum pixel and storing it in pixel.pos after multiplying it by u.pixel. And u, if you remember in the last statement, we had imported astropy.units as u. So it is actually doing in the units of pixel. And then HPC underscore max will be equal to AIIA. What the second line is doing is that the word coordinate system has to be converted into to say word another format, and for that we are using the last this line. So in this case, what it is doing, it is transforming the given pixel coordinate into helioprojective Cartesian coordinates, and HPC coordinates represent a 3D coordinate system centered on the sun. And in this particular case, it is observer dependent, and then the observer is assumed at the center of the earth. So you will, if you will see, there are many coordinate systems which are there, and there is a need to convert from one coordinate system to another according to the image has got some coordinates x and y, so it has to come back to its own position after that. So please note down, it is very difficult to explain this in very limited time. So for time being, please note down these two lines and run it, and then I will explain the next part. So once we do this, we have got, we create a new image, new figure, add a subplot with the axis given by the AIIA image. So what we do, fig is equal to plt dot figure, ax is equal to figure dot add underscore subplot, projection is equal to AIA. So it gets back the same kind of, say, parameters as was given in the original picture. AIA plot is equal to axis is equal to AX, and then AX dot plot underscore coordinate is with the within the bracket we have the parameters like HPC underscore max, BX, fill style is none, and the marker size is 10, PLT show. What it is doing is that it has identified the pixel with the maximum brightness, and it is labeling that with a cross. So it overlays a black cross to indicate the brightest pixel. I think it will be more clear if I go to the image and try to tell you what this program has done. So in this case, this is the helioprojective latitude solar underscore solar dash gamma, and on the x-axis we have got helioprotective longitude solar x. The latitude in this case on the x-axis are from -1000 to 1000, and on the y-axis also from the -1000 to 1000. And this is AIA 193 angstrom image, which is there in the data of sunpy. It is observing the whole disk of the sun and then finding the brightest pixel and then marking it with a blue cross. Is this point clear? I can go to the previous slide. In essence, we can say that the image was taken from the repository, and in that, the program was written to find the brightest pixel on this particular image, and then marking that with a blue cross. And that can be done in order to know, to pinpoint the position from where there might have been a flare emanating on the disk of the sun. And in this case, as an example, please try FIDO to access data for a specific date and time. Like in the first problem, you can say try you can try FIDO search to basically get time between 28th of July to 29th of July. It can be any date. For any duration, it can be done. And use the instrument AIA, which is one of the instrument which is available for data. And in the wavelength 171, we have done a wavelength 193. we have taken a wavelength of 193 angstrom. So as we studied that data is collected in different wavelengths for different specific reasons, and this can be done for a case study, which can be for any wavelength, and that can also be done in this regard. Okay. So I think we need to understand the second part in more detail, but I think essence should be the applicability of sunpy for different applications must have been, I think, demonstrated by these examples. And I will be sharing these files to you. So don't worry in case you are not able to run the program, but there will be exercise to utilize or tweak these programs for a specific application, and also to explore more applications of sunpy, because these are just two illustrative examples, but there are a plethora of examples, illustrative cases which are applicable, which are given, and which can be tried and understood with the kind of libraries which have been introduced to you. And that will be a good skill which to analyze these kind of data of the solar activities. Okay. So now I will be basically, we can have a small Slido, and we can try to see that it is sort of a recap on few things, not on the program, but otherwise. So I will request everyone to please join the Slido quiz. Join the quiz at slido.com with this code 199, please. May I request for a few extra minutes for completing this task to the organizers?
Yes, ma'am.
Okay,
Sure.
thank you so much. Thank you. We have around 55 participants, so everyone is requested to join fast so that we can begin quickly. It won't take more than 5 minutes, so please, all are requested to join in. We have 107 who have joined, so please join fast. So we begin with a solar flare is a huge burst of energy from the sun, a tiny explosion on the sun surface, a cool place on the sun surface, a solar wind particle. And the correct answer is done correctly by 83% of the participants. Moving further on, a characteristic of a solar flare is it can only occur during night. These emit extreme UV and X-rays. These can happen due to planetary motion of the Earth. These can cause sudden cooling of the sun. So the correct answer is by 93%. These emit extreme UV and X-rays. Moving further on, what type of data can be analyzed by the sunpy? Visual image of the sun only, solar wind data exclusively, spectroscopic data from solar observations, time series data, images, and other solar observational data. So we have a correct answer by 80% of the participants. Which Python library does SunPy rely on for handling solar data in the time series format? NumPy, Pandas, Matplotlib, AstroPy. Answer to this is Pandas. Which SunPy module has capability to convert solar data between different coordinate systems? SunPy.magnetic, SunPy.convert, SunPy.coordinate, SunPy.transformation. SunPy.coordinate is the correct answer by 70%. Which of the following is not a use case of the SunPy library? To import solar data from FITS file, to transform coordinate systems, to visualize solar activity with time series data, to control solar telescopes directly. Correct answer by 80%. That is good. So we have some results by 6 who have secured all well. Parthmesh, Anne Mary Wilson, Karthika, Sujal Prajapati, Johara Jafar. All these with the 6 out of 6 and with the least time of Zenzen. I remember, I think the first one was there in the previous quiz also. And the hardest question, which was not answered by many, was which Python library does SunPy rely on for handling solar data in the time series format? Okay, so with that, I would like to acknowledge Professor Rajmal Jain, Dr. Arun Avasthi, Mr. Tuchar, and all the group members who are actively working on the solar research. And I'm thankful to Professor Shetty, all the IIPT sub RC08 and IIPT Central President Professor P.K. Aluwalia ji and Dr. Rekha Gorpade and everyone who is, and the Krittika team also, who have all been instrumental in organizing this wonderful, say, winter school in which everyone is going to get hands-on experience also. I'm thankful to Principal Gargi College and my colleagues and students, and I acknowledge the sunpy community and the various initiatives and organizations from which the data is derived. So thank you very much, everyone, and thank you to all the participants. Today the time was quite less, so I feel I also feel that it needs more practice and more time has to be spent on this. So in case anyone is more interested to do any kind of project, they can get in touch, and I think I will be happy to help them. Thank you so much.
Thank you, ma'am. That was a lovely hands-on experience for the students who have already done it. And those who have not done it will surely try it. And thanks from the whole team of IAPT.
Thank you so much.
Thank you.
Thank you so much for the opportunity. Thank you so much,
Th-
ma'am.
Thank you, ma'am, for accommodating in shorter time because of the last minute changes. Uh, Thank you very much.
Thanks a lot. Thank you very much.